Good morning, good afternoon, and good evening, everyone. Thank you for joining us for today's presentation, Modeling of Wastewater Treatment Plant, The Journey from West to Twin Plant, Part 1. Please allow me to introduce today's presenters. We have Ms. Ann Quenzer and Mr. Ryan Sanford. Ms. Quenzer is the head of U.S. Urban Department, leading a team of our wastewater process engineers, urban hydrology, and hydraulic modeling engineers, and she is also a senior solution architect specialist. She is principally involved with hydraulic analysis and design with emphasis on wastewater collection and stormwater systems. Ms. Quenzer has extensive experience and expertise using DHI's Mike Urban, as well as integrating GIS data and modeling applications. Mr. Sanford has experience in West process modeling, DIMS core controller design, wastewater process design and simulation, water treatment, and oil and gas process engineering. He is also experienced on Mike Urban and Mike 21 hydraulic modeling support, project management, and data analysis. And with that, I now hand it over to you both.
Thank you, Barb. I'd like to just introduce a couple other people that are on our wastewater team. Peter has 35 years of experience in chemical and biological process in relation to wastewater treatment, planning, and industrial environmental impact, cleaner technology, as well as efficiency and optimization of wastewater treatment plants. Fabio and Enrico both have PhDs in wastewater modeling, along with the modeling of numerous systems in Europe. They provide quality control for the West model calibration in the US projects. Dylan and Arnold are also part of our US resources for digital solutions. We also have numerous staff around the world that help with AI, machine learning, interfaces, and optimization. I want to just take a brief moment because some of you may not know who DHI is. Our main office is located in Denmark. We have a strong presence throughout Europe as well. DHI has offices in numerous locations around the world, including Australia, Asia, and the Americas. Our US team is headquartered in Colorado. DHI is an independent research and consultancy organization that promotes technological advancement in areas relevant to water, environment, and health. Every year, DHI invests a considerable part of its resources into research and development to extend the knowledge into various fields related to water, environment, and health, and to prove its methods and software. We offer a broad range of consultancy services and reference material, as well as software and hardware products and tools, and the services are offered in the different areas that you see here on the screen. DHI's Urban Water Department has partnered with public utilities around the world to advance the optimization of collection system operations and storage, as well as wastewater treatment operations, both with the goal of enhancing effluent quality, minimizing operational costs, protecting public health, and reducing urban impacts on the environment. The team includes wastewater process modeling specialists, as well as hydraulic and hydrology modelers. Next slide, please. Our Urban Water Department focuses on the full system of water modeling. We were the first to complete a surface water pipe network integration model. The urban hydrology is modeled as it flows over a 2D system. The infiltration and inflow enters the pipe through the cracks, the breaks, the manholes, etc. The infiltration and inflow, along with the daily sewage flow, is then hydraulically routed to the wastewater treatment plant. The effluent from the plant is then modeled in the receiving water body, such as a river, lake, ocean, or wetland. The integrated modeling approach helps the utility with flow forecasting, reductions in sanitary or combined sewer overflows, treatment process optimization, energy reduction, and water quality in the receiving water. Next slide, please. This schematic represents the integrated model as discussed in the previous slide. The standard West library focuses on the block indicated where it says wastewater treatment plant. The integrated urban water model allows the upstream hydrologic catchment and a sewer model, as well as the downstream river model. DHI's digital twin plant uses the integrated water system library and can be used for scenario analysis and future forecasting. Next slide, please. Complex dynamic systems can be coupled with DHI's Mike Plus software to enable flow forecasting and predictive control to reduce combined sanitary sewer overflows. And the West model can also be coupled with DHI software to analyze water quality in the receiving water body. I'll go ahead and do the next. Yeah, I think that animation didn't work out so well. We'll work on that for this afternoon. All right, go ahead and go to the next slide. Today we have 2 case stories to present, and Ryan will do the presenting of the different case stories. We will follow along with the various modeling exercises completed for the 2 projects. First, we will define the opportunities that the different agencies have presented. Next, we will briefly show the model setup. And if you want more details on how to actually do a WES modeling and in a detailed instructional case, I would refer you to our online WES modeling class that will show you at the end of the class and how to get that on the Academy. Number 3, we'll show you how to set up the problem within the model. And number 4, we will run the different scenarios. And finally, we will analyze the results and draw some conclusions. Next slide, please. The 2 case stories we will discuss in detail are based in the US and the other one is in Denmark. The first is a planning project and the second is a project that is currently being implemented. The planning project is reviewing the plant process in anticipation of the total nitrogen and total phosphorus permit levels changes. The implementation project is a capacity expansion project that needs to be expanded within a given footprint. The 2 case studies demonstrate common problems found in wastewater treatment plants around the world. So there's nothing unusual about either one of these. Next slide, please. In the first case study, the challenge will be to plan for the new total nitrogen and total phosphorus requirements without disrupting ongoing projects within the facility. The facility doesn't know when the permit limits will change or by how much, but they do know that they're coming. DHI is working closely to consider the overall utility objectives. In the Denmark case study, the challenge is to treat the extra influent wastewater load that they anticipate within the existing volume of the wastewater treatment plant. The new load is coming from a new development with numerous industrial sites. So the objective of the utility was to keep the extra load within the plant and not add any extra capital expenditures. This is due to the future plans to close this current facility within the next 10 years. My final slide. It is critical to supplement master planning with optimization modeling exercises. The wastewater process models help with the system understanding. It can answer the question, does the plant perform as expected? Are there areas that are not functioning as designed or anticipated? The scenario analysis within the process model can help determine how the plant performs under various conditions. The overall wastewater process model helps with the plant upgrade decisions, optimization of the biological and chemical treatment, as well as the energy consumption reduction. Webinars 2 and 3 that are coming up, which we encourage you to join us, will build on this model implementation with advanced controllers and the online digital twin modeling systems to further explore the optimization and control of wastewater treatment plants, as well as future forecasting. And with that, I will let the fun part begin and I'll pass it off to Ryan. So thank you.
Ooh, thank you. Yeah, once that opportunity has kind of been identified and we've decided that we'd like to build a model, there's a lot of considerations, and we always want to come back to this kind of theme as to why we're modeling, and that can really help set up the project for success. So I'm just going to head over to our demo. So this is the nutrient removal planning project that Ann was referring to in the US, where we're not just hired to build a model, right? We're hired, all modelers are hired for to use a model to draw some conclusions. And in this case, we want to use our wastewater experience and controls design experience to help evaluate options for this plant. So let's just start by running probably more than 2 days. So I'll run a steady state model of this plant, but it's pretty simple. I haven't put too much detail into this yet, and that's because it's a planning study and we're just looking at some steady state options. There's a simplified headworks where we're combining 3 different flows: primary clarifier, trickling filter here in the middle, kind of an older technology that we'll evaluate a little bit. Activated sludge system, only one of these 2 is operational. The other one is a full-size spare. So ASU1 right now is set to be online, ASU2 is offline, and then secondary clarifier to return solids back to that activated sludge process. And now I can continue running. I set up a few dashboards here. We can watch kind of the biology grow in the trickling filter, look at the activated sludge system. If I take out the measured values, I'll zoom in a little bit. So we're currently working with about a day of retention time, or solids retention time, so low sludge age. And again, I can zoom in. The effluent quality here tends to track the measured values for what we're interested in, so that I would say that this looks like it's calibrated, at least at first glance. And you'll note that total nitrogen leaving the plant up here is like 60 milligrams per liter. So that's kind of going to be our main focus, is how can we reduce that, using the biology and the system that already exists at the plant. And we have this dashboard too, so we can kind of at a glance see how different simulation runs affect return sludge and waste pumping, aeration energy, and here it is again, aeration energy kind of on the big dial in the middle. And also I have the pumping for the trickling filters, because that's not a cheap expense that we want to ignore. So, okay, that was the first run. Kind of gave us an idea that probably our influent file is okay, and that's, I tested the primary clarifier and looked at the primary effluent compared to measured values, and I would say we had good calibration on the front end, and then secondary clarifier or secondary effluent and wasting rate all kind of matched up. But the one thing that didn't quite calibrate at first was this trickling filter. But before calibrating it, I want to just talk about in general what calibration means. I mean, we need to have a model that is calibrated to the plant so that we know, or that we have some level of confidence that this model emulates the real system. But at the same time, we're doing a lot more as we calibrate. This is part of why we model. It's to kind of calibrate our understanding of the plant. And building just a simple steady state model to run and emulate the processes helps identify knowledge gaps. A lot of times I'll build a model and then realize, wait a second, we actually don't know how solids are controlled at the plant. How often is an operator actually looking at this mixed liquor suspended solids concentration and adjusting wasting rate? Is it automated? Is it a daily or weekly check? Is there even a VFD on this pump or valve? How can it be controlled in practice? And then how's the return sludge controlled? Things like that. So it kind of, the calibration phase kind of uncovers these missing pieces that you may not have known, that you didn't know. And then always please present your model to the operators, not just the project team and the engineers, but talk to the operators, because they're going to point out things that you don't think are relevant to a model. One time something came up and our operator was like, hey, why don't you include the skimming stream from the primary clarifier, right? Because we take out, we skim basically grease off the top of the grease and soaps basically from the top of the clarifier, and usually it makes its way into the primary sludge. And okay, maybe it's a really small stream, 100 gallons per day or something like that, and we're treating 10 million gallons per day. So it might not be hydraulically relevant or something like that, but just the fact that an operator brings it up tells you that either there's a problem with skimmings, or it has an effect on the primary sludge and maybe the digester, or what they can do with that sludge, or maybe the primary clarifier operation and foaming. And anyways, it's not a discussion to just table and kind of ignore because it's not directly relevant to the model, but you have to pay attention to those kind of things because they are relevant to the practical application, which is why we model. We're trying to come up with some real world solutions in this case. We're also trying to use this model in the long term for converting this into an automated model and having a digital twin online or online controls. Okay, back to that calibration off the soapbox. The trickling filter is not that widely used of a model, at least in my experience. So our whole team kind of dove into this. The PhDs, modelers that Ann was referring to, our Italian stallions, helped us out, and we kind of dove into all these different parameters to find out which values can be left at the default, and which ones do we need to change to kind of fit the data and just general operation that is kind of reported from the plant. So we noticed that the way it's set up now is not hardly doing anything. It's taking out 10% of soluble COD from the front end of the plant, or from the primary effluent, and converting that to active biology. And from operator reports, that's just not accurate. So after a lot of trial and error and kind of reimagining this model, we found that this diffusion coefficient for oxygen, and the one for soluble substrate as well into the media bed, was too low. So if I change that, and these are assumptions that we need to check, right? If you're not familiar with a trickling filter diffusivity coefficient, you have to decide and defend if it makes sense to increase that to 0.0015 square meters per day, and determine that that's within an acceptable range, or a practical range. So if I change that and rerun this model, it's down here in this table data, but I made a small calculator variable. So now our soluble COD removal is up to 40%, significantly higher, and closer to what our operators are telling us they take out in those filters. We'll note that there's really no change to SRT or DO, secondary effluent quality, and here's that dashboard. I wanted to point out that there's very little change to the aeration energy required when we change the filter performance there. So that tells us that maybe there's some spare capacity in this activated sludge system, because whether or not we took out the COD in the trickling filter, the activated sludge tank seems like it didn't notice. So that's kind of the final bit of calibration. Calibrate our understanding, but also calibrate the individual models within the plant. Ann referenced it, but for more information, there's there's I think 3 West courses. There's kind of a beginner, a self-paced free one, and an advanced West course. So if you want to learn how to do this on your own, you gotta take the class. So that's how we set up the problem. That's how we set up the model. Now we got to set up the problem. So some problems that we can solve modeling, or why we model, are we can assist with design. If we're making a new wastewater treatment plant, or we're upgrading a wastewater treatment plant, but mostly what we use it for, at least in my practice, is optimization, and that's modifying how we operate the plant, or modifying how the plant is laid out, but without really changing or redesigning the plant. And then consider all these other things as you're asking yourself, why are we modeling? Should we be minimizing chemical dosing? Is that a major consideration? If so, or greenhouse gas emissions, if any of these become more relevant, then this varies. Like I said, this is a simple model. It's going to have to be updated to capture those like chemical dosing, and add a controller to kind of see how much chemical is being dosed, or how much greenhouse gas emissions, nitrous oxide emissions from the nitrification, denitrification. Okay. So those are some problems that we can try to solve from modeling. The next step is setting up the problem, and it's not hard sometimes to set up an experiment, but I think it's important to make a good hypothesis, and then it kind of becomes more difficult as you try to evaluate your assumptions. And the execute simulations part is easy. It's the science and the engineering that's the hard part. So yeah, it's a combination. We're going to run a lot of experiments, so that's why it's a bit of a science. but we're really looking to draw practical conclusions from the model. So that's also an engineering practice, and it is a bit of an overlap. So let's make our hypothesis. If you remember, it's an if then because statement, or that's how I was taught it at least. And the simplest way in this case, because I know I want to take out more total nitrogen, or at least some ammonia, if I increase SRT, presumably by modifying this MLSS controller, which will just reduce the wasting rate, then I will enable nitrifiers to grow and nitrify. And that's the easy part, right? Pretty much anyone who's in a wastewater engineer or operator knows that higher SRT is good for growing nitrifiers. But the nuance kind of comes into that because part of the statement. So why do we think that this is feasible? And start to lay out some of the assumptions that we've made in this model that are going to need to be checked. So if I increase SRT, I'm going to have nitrification. Well, I know that that's going to require more oxygen. Is this model even set up to evaluate aeration rate? Well, we had an aeration energy calculator, but these are just small DO controllers. They're not actually controlling a blower in this case. So we're working under the assumption that there is sufficient blower capacity for this job. And that's something that we're going to have to evaluate. That's not a fair assumption. We can make it for now and run this test, but we have to keep that in mind. Same thing with the secondary clarifier. If we have more solids, we're going to have to settle out more solids. Can the clarifier handle that? Are we set up to evaluate that? And how critical is it? So questions like that start to get more important, and you can't just like state these assumptions and forget about them. But in this case, let's just try it. So right now we have about 1,200 milligrams per liter MLSS. I'm going to increase to 3,000 and then rerun. So I'm not going to change anything else yet. I can see our bugs growing here. Oh, they're up to 4,000. So this controller probably needs some tuning. It took, let's see, 5 days before it adjusted, but it's a steady state run, so we just care about the end result, really. So increasing to 3,000 gives us SRT of 5 days, and remember, we're only using one of these two tanks, so opening the other one will almost double the SRT. And here's the more interesting one. Let's hide a few items. We don't care about the measured data as much anymore because we're not trying to calibrate to that anymore. But this green curve is the ammonium in the secondary effluent. And we see it's a sign that nitrifiers are growing and starting to take up ammonia, if I zoom in just to the end. So with just that change, we're now, this indicates that we're able to reduce ammonium concentration in secondary effluent down to 2 milligrams per liter. We'll see what else happened. We also see that this yellow line, if I compare it to this purple, let's add some more things to make it more obvious. That's secondary effluent solids, TSS. And this was the run before when it was calibrated. So we went from around 12 to 30. So that tells me that I have to revisit that assumption about the secondary clarifier. But overall, it just gives us a little bit of a gist that we can get some nitrification from this plant. What I really want to know is, can I also get denitrification from this plant? So we'll continue to make hypotheses and modify the plant. Here's a different model where it looks almost exactly the same, but I modified ASU1 and ASU2. Oh, first I opened this valve, so now 50% of the flow goes to ASU1 and 50% to ASU2. So now ASU2 is online, and I took each of these tanks and split them like 35-65, something like that, 40-60 maybe. So the first section is not aerated, and then there's a baffle, and the second section is aerated. And the first section is anoxic now because I'm recycling. This was the third change. I'm recycling mixed liquor from this combiner over to this combiner. And remember why we're modeling. So let's take some time as you do this to note some assumptions. One of them is that I'm assuming we can put a baffle in this tank. You have to look at the geometry of the tank and decide if that's even a good idea. I'm assuming that we can get mixed liquor return either from here or somewhere else and get that back to the front end of the activated sludge units. And those might not be good assumptions. They always have to be checked. But this will tell us something about the capacity of our tanks, regardless of the practical implications of moving sludge around and adding baffles. This will tell us if these tanks are big enough. Okay, so we've made our second hypothesis. Let's run this plant or the simulation. Now that I've got 2 tanks online, I think we have longer SRT. And we do 9 days. And the same solids, 3,000 milligrams per liter MLSS. Wasting rate has significantly reduced from the actual. And then, again, we don't need our measured data anymore as much. It's not as relevant for these runs. But here it is. Total nitrogen is down to 36 milligrams per liter. And I don't know if I pointed it out in the last model. I'll just go back to it. It's sitting right at 60 milligrams per liter. So in the original model, where all we're doing is nitrifying. So that tells us that there's no denitrification, right? All the ammonia that's converted to nitrate and nitrite comes out as total nitrogen. But now we're taking out almost half of it. We're down to 36 parts. That tells me that there's some capacity in these tanks, right? We can probably get some good denitrification going. It's not gonna, I mean, we don't know what the total nitrogen permits are gonna be, what the targets are, but we can probably assume that they're gonna be less than 36. So we're not quite there yet. We're gonna need more denitrification capacity in this system. That's kind of a boundary, not a boundary condition, but that's one main conclusion that we can draw from this. But one thing I want to test is what happens if we bypass these trickling filters. We know that they're old, that they're in need of repair, and they're expensive to operate because you pump up and you pump around. So let's see what we can do. And we noticed earlier that they weren't as effective as we expected in our baseline run. And then when we increased the effectiveness of the filters, we noticed that the activated sludge system didn't change that much. So I've increased bypass to 90%. So I haven't completely shut them down, mostly because I don't want to throw an error into this. If I feed no flow to a trickling filter, it's going to dry out and we're going to have problems. So I'll leave a little bit of water in there. And a rerun. I meant to show this in a different way. Let's see if this works. There it is. So I meant to pause the last model halfway through and then make that change. So I actually did the opposite. So this first section is when we're running with 90% bypass, and then I increase the bypass, or I reduce the bypass back down to 10%, and then the total nitrogen in secondary effluent jumps back up to 36. So I know it only goes from 36 to 32, maybe a 10 or 15% reduction, but it still tells us something. I'm going to rerun this one more time just to make it more painfully obvious. 1 day, 2, 3. Now I'll drop it. Okay, I failed again. Let's stick with that last run. So anyways, we see this change in total nitrogen, and that tells us pretty much only one thing. So if we bypass the trickling filters and we can get 4 milligrams per liter less nitrate, basically, that tells us that we're carbon limited in these tanks, and that, you know, taking out carbon in the trickling filter is maybe not that useful of an exercise anymore. So that's not to say currently the trickling filters aren't needed, because that's not how we operate the plant. And one thing you probably, I don't know if I mentioned this, but aeration energy almost doubled, or more than doubled. At one point it almost tripled. Now it's back down to 16,000, but it started out at 6,000 kilowatt hours per day. So that's a pretty major consideration. How much power can we put into this process? How much is that going to cost? And also, do we have the blower capacity to even take that much more capacity? Or, I mean, yeah, can you put that much more power into the blowers, and is it effective? So those are questions that still need to be answered. But another conclusion that we can draw, besides the fact that we don't have enough volume here for full denitrification or enough carbon. So that was the first conclusion, is that we're going to need more volume, and we recommended either, in this case, I think an Animox, side stream Animox, possibly side stream like intensification process instead. But that the Animox will significantly reduce the amount of carbon that's needed for the denitrification in these tanks, and it also has a nice benefit for aeration rate. But the other conclusion that was a bit more surprising was that these trickling filters, if they're near end of life, it might not make sense to put $20 million into the maintenance of these things. You know, if they need full new media beds and they need to be reinforced, the concrete or the tanks themselves, we need to reconsider that allocation, because that's a lot of, you know, ratepayer funding that we can allocate towards longevity of this plant and moving towards a denitrifying process. Time check. Okay, so that's how we set up the problem in that project. In this other project, we're going to look at these more advanced experiments. You're not supposed to see the results yet. We've got these 5 advanced experiments that we can use in West, and this is the model for that second case study that Ann mentioned. This is a project in Denmark where it's an implementation. We know they're going to get more flow, more load, and we need to see how much more capacity can we squeeze out of this existing facility. So there's a bunch of denitrification tanks and 3 main aeration tanks. And this project decided in the design phase, kind of in that phase, or the design and planning phase, kind of like what we're just doing for the American project, but the engineering team decided that these 3 denitrification tanks would actually be swing zones, and actually the final project ended up making lift tank 3 also a swing zone, aeration tank 3. Anyways, my point is, this is kind of the final design, or the layout that we're anticipating. And what we now need to do is prepare it for operation. And if I don't have to show it yet, we've got these 3 kind of denitrification controllers, and they're talking to, I don't know, one main controller. There's this forecast controller that's talking to those controllers, all of which talk to these blowers. And then if I unlock it now, we can see there's actually a lot more controllers. There's DO discussion going on between these 2 controllers for the DO setting for the aeration tanks, and of course mixed liquor control, RAS flow, and chemical controls. So to tune each of these, you can just start up the plant and start tweaking valves and parameters, but that's a lot of work. So what we can do is change them in a virtual space instead. But if you look at each of the controllers, there's Y min, Y max. These are measured values that are coming in. So you actually probably don't set those. Well, yeah, in this controller we do. There's U min, U max, the controller output. There's these set points depending on which controller model is behind this block, which can be custom written depending on what kind of controller you want to build. Could be PID, could be on off or feed forward. My point is there's a lot of settings and parameters that we're going to need to select. And one way to do that is to use parameter estimation. So if I go to the analysis properties, this is one of the advanced experiments. They're grayed out up here because I have one open. But in this case, I've selected the parameter KO for each of the tanks. So it's a saturation coefficient for oxygen in the activated sludge, which can be different from plant to plant. It's not always the same constant. And you select an objective function. In this case, we're going to use secondary effluent ammonia and nitrate, and we're going to ask West to try to minimize the difference between the measured and simulated effluent values by changing these parameters. You select the solver, set up your output, and then it automatically generates all these runs. That one's highlighted, so it's probably basically done running after 29 simulations, even though it ran 62. And here are the results. So the mean difference in effluent nitrate between simulated and measured starts out at like 2.5 milligrams per liter and makes its way down. And through the iterations, it's going to approach zero. Not always. In this case, it's a pretty cut and dry parameter estimation. And this is through the iterative solution or iterative process. So throughout each bar represents a different simulation run. We've got a similar plot over here where for each run, West selects a different KO value, saturation coefficient, and we can see it drops all the way down basically to zero. Actually, it looks like it does hit zero. I should have made a bound so that it couldn't go that low. And then kind of oscillates around 0.2 until it flatlines at 0.2 after maybe 30 runs. And this is the final plot. These are time series now, where the dots or the squares represent the measured values and the curves represent simulated values. I would argue that this is an overfit, but it shows that West was able to select a KO that satisfies these objective functions. The idea is that you can set up West to run a lot of experiments and automatically change parameters for you. So that was one of them. We saw that it ran like 66 or something like that, but now we're going to run a lot more simulations. This one, I think we ran 300 simulations, and the result is this sensitivity analysis. So I loaded all of these parameters and asked Wes to wiggle those parameters and see what happens to selected objective functions. This plot shows the results for total nitrogen. So I can see that the first two bars, which is nitrate control, it's a tuning parameter for the maximum nitrate that's allowed in the secondary effluent before one of those denitrification tanks switches, or one of the swing zone switches mode. So that's obviously an important parameter. And the second one is the DO control in the aeration tank 2. And although that may seem obvious, there's 3 aeration tanks, and this is the one that has the most impact. So that gives me a starting point for tuning this controller. So I'll take those 2 parameters and then run another experiment. I'm going to ask Wes to change those 2 parameters within a given range and give it a distribution, whether it's linear or some uniform distribution or bell curve or whatever's relevant, and then start Wes will then start automatically pairing parameter sets and running simulations and giving us the results. And here we're looking at the objective functions total nitrogen, and I added another one, aeration cost. And in the x-axis, we have that parameter that we saw was particularly sensitive, DO set point in tank 2, and the nitrate tuning parameter in the z-axis. So while it doesn't, I mean, doesn't tell you how to operate the plant, right? It shows you the diverging objectives, actually, but it informs how the plant can be run. Move that back. So I don't know. One conclusion might be after 2.4 for this particular set point, we don't get that much more bang for your buck, but we do see an increase in cost. So, maybe we we set the bounds for the set point to maybe a maximum of 2.4, and depending what total nitrogen we can allow, maybe we would set the other end to 1, and then allow operators to make a selection between the two, or it kind of depends how the controller is set up, but it gives you a really good idea of where your different operating points are. And the last bit, which can be the most important, remember we're trying to come up with some practical applications, and why we model is to make recommendations for the plant, but it is still just a model, and we have to convince ourselves and our clients that the model is representative, and there is always uncertainty in input parameters. So uncertainty analysis is a good way to run basically 1,000 experiments, let West do all the work, and kind of quantify how confident we are in a given result. So in this case, we're taking, I think, influent COD fractionation criteria, because we don't have a lot of measurements on site for, say, VFA. How much of the soluble COD in the influent is actually acetate and can be quickly degraded. And sometimes that can make a pretty big impact on effluent criteria or effluent quality for a given operating point. So we ask West to go ahead and modify certain parameters. You let it, you load as many as you want, and it just increases the number of runs that are needed to get a result. And then it does a bunch of statistics that I don't remember how it works from college stats, but basically this blue line is the 95th percentile. So we can say that we're 95% confident that we will operate on or underneath that curve. And if our target was 6.5 total nitrogen, I can say with 95% confidence, based on the uncertainty in those input parameters that we selected for this experiment, that we will not exceed 6.5 milligrams per liter total nitrogen, actually in this case nitrate, that's what we're plotting, 20% of the time. So less than 20% of the time we will exceed that point. And I think that's a good result. I mean, it's important to quantify these things, because otherwise it's just a model or saying things, right? We have to have some way to defend and quantify the results that we come up with. We've got a couple minutes, but we probably want time for questions. But so 2 seconds maybe on model evaluation. Sometimes your result here is that the uncertainty is too great. We can't really deal with that. Sometimes your calibration just doesn't work, and you have to decide, does this model that we made even represent the plant that we're trying to model? I mean, usually I'm working with these kind of plants, activated sludge systems, trickling filters, primary clarifier, secondary clarifier. They're not crazy pieces of technology or membrane systems, stuff like that. But sometimes you see a plant or a process, maybe it's not even wastewater related, or maybe it's not municipal wastewater, but it doesn't conform to these standard models that come with the standard model libraries. If that's the case, then it's probably time to unpack that and build our own model, which we can do yeah, with our model editors. There's a picture of Enrico going to town on one of the model editors, but you can also just tap into the GUI or matrix and make these changes inside the West GUI.
Well, I'd like to just thank everybody again for your time. And the next webinar, Ryan, do you know when that is on the calendar?
Right
we do have 2 more webinars, one to talk about advanced controllers, and the next will be, then the final one will be actual twin plant and digital twins of the systems. We also have online self-paced WEST classes, as well as instructor-led WEST classes as well. So if you look on the Academy, you can find those, and please contact us with any questions that you might have outside of this. We're more than happy. Ryan, do you have anything else? Otherwise, I'll just say thanks.
Yeah, thank you, everyone. It's kind of hard to do a Zoom meeting or a presentation like this when you can't see everyone's faces, but all the really good questions are super encouraging. People are out there listening and thinking. That's the important part.
Yep, and the next 2 ones are going to be even more fun. So please join us. Thank you.
Thank you.